In this video, I want to introduce you to nth order differential equations. If you enjoyed first and second order differential equations, then boy, have I got some good news for you, because these are just even more of whatever those were. The general nth order differential equation is essentially this, where you have the nth derivative of some function y being expressed as a function of the independent variable y, y prime, y double prime, all the way up to the n minus first derivative of y. Okay? And of course, a solution to such an equation would be a function that satisfies that equation. Now, we also had the notion of the initial value problem, so that you not only had a differential equation, but you had some initial conditions. And you may recall that first order equations had one initial condition given, and second order equations seem to require two initial conditions, and might suspect, and you'd probably be right, that the nth order differential equation actually involves n initial conditions. You could say I know n different points that I want on my graph, but usually the initial conditions are given as at one particular t value. I know the function value, I know the derivative, I know the second derivative, I know the third derivative, all the way up to the nth derivative. Okay? No, not the nth derivative, the n minus first derivative. Okay? And as you know, each one of these derivatives at some particular value of t. Now, as we get higher and higher order differential equations, they become more and more difficult to solve. And so in this introductory class, we focus only on the simplest ones, which are linear. So the general linear nth order differential equation looks like this. Some function p0 of t times the nth derivative of y plus p1 of t times the n minus first derivative of y plus and so on, down to p sub n minus 1 of t times y prime plus pn of t times y equals some function of t. This is what is called a linear differential equation, nth order linear. Now, pointing out here that the functions p0, p1, p2, and so on are not necessarily linear functions. They're any functions of t you might want. What's linear about this is that y, y prime, y double prime, and so on appear only to the first power. They are multiplied by something, and then those are added together. This is kind of like a linear combination of y and its derivatives. It's not exactly a linear combination, because linear combinations are you multiplying by constants and then adding up. Here you're multiplying by functions and adding up. Now, in the event that p0 of t is never equal to 0, we divide by p0 of t and rewrite this equation this way, where you have a 1 in front of the y prime. Most of the theorems about nth order differential equations assume that it's written this way with a 1 out in front, so whatever was there, divide by it. That being said, we will solve certain types of equations that have something other than a 1 right there, and sometimes what you do is you divide it out, and sometimes what you do is you work with it there, depending on the situation. But we'll see in upcoming videos. The left-hand side of this equation is quite often written in shorthand, in that if you look at all that left-hand side and you say, well, let's call that L of y, it turns out that L of y is a linear operator on y. Each one of those derivatives is a linear operator when you're multiplying by the functions pi. They distribute over addition and commute with scale multiplication, so that's still a linear operation. And then you are adding those things together, which is, of course, linear. So we have a linear operator here, and then our differential equation can be rewritten as L of y equals g of t. This is a very shorthand way of writing that big, long nth order differential equation. Okay. Now, theorem, a couple of theorems here. Given this nth order linear differential equation and some initial conditions, and the initial conditions I have here are that at some point t0, I know the function value, the derivative, the second derivative, and so on, up to the nth derivative. This doesn't look like a derivative here. That looks better. So we know the n minus first derivative at t0 is equal to some value. Now, and we also know that the functions p1, p2 up to pn minus 1 are all continuous on some interval I containing the value t0. Okay. Given these conditions, then there is a unique solution to this differential equation that also satisfies the initial conditions. Furthermore, that function is continuous on the interval I, where all of the functions p1 to pn were continuous. Okay. This is very similar to what we saw with first order linear or second order linear. This is now nth order linear. Okay. The theory is pretty general. It just keeps working each time you add on a new derivative in your equation, right? As long as you're talking about linear equations. When you don't have linear equations, then all bets are off as to what's going to happen. Now, next theorem. If you've got n functions that are independent of each other and that they all satisfy the differential equation, then it turns out that the general solution to the differential equation can be written as a linear combination of those functions. So with second order, we had to find two solutions, and then you'd have c1y1 plus c2y2. Third order equations, you're going to need to find three solutions. For third order, you're going to have four solutions, and so on as we go. So nth order, you got to find n independent solutions, and then you can take all the linear combinations, and you get all of the solutions to the differential equation. If those solutions that you have are not independent of each other, then this linear combination does not describe all of the solutions. But once you get n independent solutions, you can describe all the solutions. Right? What does it mean for n functions to be linearly independent? Right? With two, it was pretty straightforward of if one is a scalar multiple of the other, then they are dependent. So, but that's not quite the case here. Some people think of it as they're independent if no one of them can be written as a linear combination of the others. But I think the easiest definition to work with is that they are independent if the only linear combination that adds up to 0 is the trivial combination, that is, if all of the coefficients are equal to 0. So these are independent if this combination adding up to 0 only happens if all the c's are equal to 0. Certainly if all the c's are equal to 0, then this adds up to 0, but if that's the only way to do it, then they are independent. Functions are independent. And we test for independence by doing the Wronskian thing, right? That this equation here, saying that, hey, what does it take to make this equal to 0? Well, the thing is, if that is equal to 0, then I can implicitly differentiate and get this would also be equal to 0, and then implicitly differentiate again, and again, and again, and again, do it n minus 1 times, and you get n minus 1 equations, all looking like some combination of functions with the coefficients c1, c2 up to cn is equal to 0. And so what we have is a homogeneous system of linear equations where the c's are the unknowns and all these y's and the derivatives of y's are the coefficients to go in the coefficient matrix. And I don't like the look of that last line, so I'm going to fix it. So that looks better. So, of course, from linear algebra, we know that such a system has a unique solution. It's a homogeneous system, so certainly it has a solution. Plug in all zeros. But if that's the only solution, that we can determine that by seeing if the determinant of this matrix is not equal to 0. Okay, if that's not equal to 0, then there is a unique solution, and these are independent. So we take the determinant of that matrix and we say, is that not equal to 0? Okay. And, you know, it's big when you have lots of functions. All right, let's do one example here. Here is a differential equation fourth derivative of y plus the second derivative of y is equal to 0. Now, I'm not going to solve that equation or talk about how to solve that until the next section, but let's just say, hey, check it out. I claim that each of these four functions is a solution. Notice if you just take the function, the constant function 1, its derivative would be 0, its second derivative would be 0, the third derivative would be 0, the fourth derivative would be 0, and notice the fourth derivative plus the second derivative, 0 plus 0, is equal to 0. It's a solution, right? Likewise, y2 equals t. First derivative is 1, the second derivative is 0, the third derivative, fourth derivative are both 0 as well, and so again, fourth derivative plus second derivative is 0 plus 0, which is 0. Sine, on the other hand, is a little different. The derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of minus sine is minus cosine. And anyway, so the fourth derivative plus the second derivative is actually sine plus negative sine, which is 0. Likewise, with cosine, the first derivative is negative sine. The second derivative is negative cosine. So you get a negative cosine there, and the fourth derivative gets all the way back to cosine again, which is positive cosine, and positive cosine plus negative cosine is 0. So sure enough, each of those four functions is a solution to that differential equation. I want to see, are they independent of each other? They certainly look like they are. But here we go, the Wronskian of those four. There's my four functions. The next line is the derivative of those things. So the derivative of 1 is 0, the derivative of t is 1, the derivative of sine is cosine. Cosine gives me a minus sign, and then I have the second derivatives and the third derivatives, and I take the determinant of this 4 by 4 matrix. Now, how do you do determinants? I do them by, what's it called? The cofactor expansion method, and I can pick any row or any column to do this on. In this one, I'm going to expand down the first column. So it's going to be 1 times, then you cover up the first row and column, take what's left. So there's a 3 by 3 matrix down here. So it's 1 times this 3 by 3 determinant, and then minus 0 times, cover up the row and column and take that subdeterminant, but it's times 0, so I don't care, plus 0 times another subdeterminant, minus 0 times another subdeterminant. All those zeros go away. So on that first column, I have only one thing I had to do was 1 times this 3 by 3. Well, this 3 by 3, again, I'm going to expand down the first column. So it's going to be 1 times this 2 by 2 subdeterminant, which would be, and then minus 0 times another 2 by 2 determinant, and plus 0 times yet another 2 by 2 determinant. But those zeros give me 0. And so it's just 1 times this 2 by 2 determinant. And so I have 1 times the quantity minus sine squared t minus cosine squared t, which is minus 1. So 1 times minus 1 is minus 1. The Wronskian of those four functions is minus 1. They are linearly independent, which tells me that the general solution to that equation looks like c1 times 1 plus c2 times t plus c3 times sine t plus c4 times cos t, and that all solutions can be written in that form for some choice of C1, C2, C3, and C4. Okay. In the upcoming videos, we will take a look at how do we actually solve these things, and I think you'll find that the methods look very much like what we did for second order equations.